Before beginning this critical analysis, I believe a transparent methodological premise is necessary. I spent months searching for scientific research that would support the criticisms of Rust that I constantly heard emerging from forums, blogs, and informal conversations among programmers. The result of this bibliographic research was as illuminating as it was frustrating. Critical academic literature on Rust is practically non-existent. This doesn't mean the criticisms are unfounded. It means that Rust has become what I can only define as a technological totem, an object of almost religious veneration in the software industry of recent years. Criticizing Rust in academic or professional settings has become almost heretical, a position that can damage the credibility or career of those who express it. The scientific research I found is systematically favorable to Rust. Not because Rust is perfect, but because structural biases exist that influence what gets researched, published, and cited. Publication bias favors positive results. Funding bias rewards research that supports trendy technologies. Peer review bias filters through reviewers who are already converted to Rust's philosophy. What you find in forums, blogs, Reddit discussions, informal conversations among experienced developers, the daily frustrations, time lost fighting with the borrow checker, projects abandoned due to excessive complexity, all of this finds no space in formal literature. It's as if two parallel realities exist. The academic one where Rust is the perfect solution, and the practical one where Rust is a tool with significant trade-offs. Science should be the study of doubt, critical interrogation, dispassionate analysis of advantages and disadvantages. Instead, too often in the technological world, science becomes marketing disguised as research, confirmation of pre-existing biases, social pressure toward intellectual conformity. Some of the criticisms I will present are philosophical and conceptual, like the concept of limits as limitations, and therefore don't have a strictly scientific nature in the empirical sense. But this doesn't make them less valid. The philosophy of language design, the impact on programmer creativity, the cognitive implications of complex systems, these are legitimate questions that deserve discussion even without controlled experiments. I am not a professional programmer. This analysis stems from months of reading, study, and critical reflection on a technology that is presented as revolutionary. If my point of view appears superficial or lacking in deep practical experience, I am here to be enlightened. But I believe that sometimes the perspective of someone looking from the outside, not emotionally involved in the ecosystem, can offer insights that those immersed daily in the technology might not see. What you are about to hear is not the absolute truth about Rust. It is simply the point of view of someone who wants to look from a different perspective than everyone else, who wants to ask uncomfortable questions, who believes that independent critical thinking is not only legitimate, but necessary in an industry too often dominated by technological trends and hype. I don't believe this is a stretch. In fact, I believe it is due. In recent years, Rust has become more than just a programming language. It has become almost a religion. Its supporters don't simply describe it as a useful tool, but as the definitive solution to systems programming problems. Memory safety without garbage collection, zero-cost abstractions, concurrency without data races, slogans that resonate like mantras at tech conferences worldwide. But what happens when we analyze Rust beyond the surface of marketing? When we shift attention from enthusiastic tweets to the trenches of production code? When we listen to the voices of those who have spent months fighting daily with this language? The thesis I want to support today is provocative, but I believe necessary. Rust represents a step backward in the evolution of programming languages. Not because it is technically inferior, quite the opposite, but because its design philosophy prioritizes theoretical dogmas over practical productivity, imposing artificial limits that stifle innovation instead of facilitating it. I'm not suggesting that Rust is categorically bad or useless. Every tool has its place in the technological ecosystem, but the industry needs an honest conversation about the real trade-offs of this language, free from the uncritical enthusiasm that often characterizes contemporary technical discussions. The fundamental problem is that Rust is presented as a universal panacea, when in reality it is a highly specialized tool with enormous hidden costs. These costs manifest not only in daily productivity, but in the very ability to innovate and experiment with software architectures. Let's start with the most fundamental question. What does safety really mean in programming? And when does this safety become a cage that prevents evolution? Rust operates according to a principle I would define as paternalistic. The language knows what's best for you and imposes rigid constraints to protect the programmer from their own mistakes. This philosophy has deep roots in type theory and functional programming, but when applied to a systems language, it produces unexpected and often counterproductive consequences. Consider for a moment the historical evolution of programming languages. Assembly gave total control, but required manual management of every single detail. The C language introduced powerful abstractions while maintaining direct memory control. C++ added object orientation and templates, enormously increasing expressiveness. Java and C# brought garbage collection, eliminating an entire class of bugs at the cost of reduced control, but with enormous productivity benefits. Rust breaks this natural progression. Instead of simplifying or abstracting, it introduces a new level of complexity. A type system so rigid and pervasive that the programmer must constantly negotiate with the compiler to express concepts that in other languages are natural and immediate. Here we arrive at the heart of the problem I want to highlight. Rust's limits are not simply understandable technical restrictions. They are true barriers to the conceptual evolution of code. They are obstacles that prevent software from growing and adapting organically to the needs that emerge during development. Take a self-referential data structure, like a binary tree node that must maintain references to its parents and children. In traditional languages, this concept is expressed directly and modifiably. The expert programmer knows how to manage memory, knows when and how to deallocate, knows how to implement automatic management patterns when necessary. In Rust, this conceptual simplicity explodes into architectural complexity that pervades the entire design. We are no longer writing code to solve our original problem. We are writing code to satisfy the needs of the Rust compiler. Every design decision becomes subordinate to the limitations of the type system. Rust convinces its users that this complexity is necessary for safety. But is it really? Other languages manage complex and sophisticated data structures without requiring the programmer to become an expert in advanced type theory. Go, for example, has garbage collection and simple pointers that allow immediate expressiveness. Swift has automatic reference counting that manages memory without excessive verbosity. Even modern C++ has smart pointers and RII that automatically manage many use cases without Rust's characteristic verbosity. The fundamental question becomes, are we really solving real programming problems, or are we creating new artificial problems to justify the existence of our complex solutions? Are we improving software quality, or are we simply shifting complexity to different areas? Consider developing a game engine, one of the domains where performance is critical and where traditionally Rust should excel. In traditional languages, you can quickly experiment with different memory architectures, pool allocators for objects with similar lifetimes, stack allocators for temporary data, custom memory managers optimized for specific patterns of your domain. You can prototype an idea, measure it, iterate quickly. In Rust, every experiment must first pass through the borrow checker. Instead of focusing on the crucial question, is this allocation faster for our specific use case? You must first solve how to convince the compiler that your solution is safe according to the language's rigid rules. The result is that many teams end up accepting suboptimal solutions because they work with Rust, instead of pursuing the ideal optimization for their domain. This pattern repeats across different domains. Database engines that use less efficient indices because they are more compatible with the ownership system, networking libraries that introduce unnecessary data copies to satisfy borrowing constraints, machine learning algorithms that sacrifice critical performance to guarantee compilability. The irony is palpable. A language designed for superior performance often forces decisions that compromise performance to satisfy artificial type system constraints. Rust's ownership system is often presented as a conceptual revolution that finally solves memory management problems elegantly and definitively. This appealing narrative completely ignores a crucial aspect: the massive cognitive cost of daily implementation. Every programmer has a limited amount of mental attention during development. This attention is a precious and scarce resource. In traditional languages, this attention can be dedicated entirely to business logic, algorithms, architecture, solving real domain problems. With Rust, a significant portion of this mental attention must be constantly reserved for managing the type system, ownership implications, lifetimes, conversions necessary to satisfy the borrow checker. It's like trying to solve a complex mathematical puzzle while someone constantly whispers grammar rules in your ear. Consider the seemingly simple act of passing a list of strings to a function that will modify them. In intuitive languages, this concept is expressed naturally. In Rust, the same concept becomes an in-depth seminar on ownership, mutability, borrowing, and lifetimes. We're not just writing more code, we're thinking about completely different concepts orthogonal to the problem we wanted to solve. Borrowing complexity doesn't grow linearly with project size, it grows exponentially. When you start having data structures that refer to each other, every relationship becomes a multi-dimensional puzzle of lifetimes and ownership that requires deep architectural planning. Imagine implementing a simple model view controller pattern, one of the most basic architectural patterns in programming. You should have a model that contains data, a view that displays the model, and a controller that mediates between the two. In traditional languages, these are three objects that pass references naturally and modifiably. In Rust, this simple pattern becomes an exercise in complex architectural engineering. Who owns which piece of state? How do we manage the lifetimes of relationships? Should we introduce reference counting, asynchronous event systems, message passing between components? Every architectural choice gets distorted by the needs of the ownership system. The result is that we spend more time designing for Rust than designing for our problem domain. Software architecture becomes subordinate to language limitations instead of business needs. Rust supporters often argue that once borrowing is learned, it becomes natural and fluid like any other aspect of programming. This optimistic claim ignores two concrete and measurable realities that emerge from practical experience. First reality: learning requires months of intensive dedication. A senior developer with decades of experience in other languages can take 6, 12, even 18 months to become genuinely productive in Rust. This isn't learning new features or new libraries. It's fundamentally rewiring how we think about code, how we model problems, how we express solutions. Second reality: the struggle continues even after learning. Even Rust programmers with years of experience regularly talk about fighting the borrow checker, having to redesign architectures to satisfy the compiler, compromises forced by system limitations. If after years of daily experience you're still fighting with your main work tool, maybe the problem isn't your competence. Maybe the problem is the tool. Every hour spent learning the specific quirks of the borrow checker, every day dedicated to understanding how to convince the compiler to accept your solution, every week invested in refactoring to satisfy lifetime constraints, all this time is subtracted from activities that could actually improve software quality. Instead of learning advanced algorithms, scalable architectures, specific domain knowledge, testing best practices, actually useful optimization techniques, the Rust programmer must dedicate significant mental energy to skills that exist only in the context of a single language. Rust isn't making programmers better in general. It's making them better specifically at Rust. There's a fundamental and important difference. An algorithms expert can apply their knowledge in any language and domain. A Rust ownership expert has developed a highly specialized competence that doesn't translate to value outside that specific ecosystem. Talking about compilation times might seem like a secondary technical detail, but it actually touches the heart of productivity and the creative process in modern software development. The right compile, test, modify cycle is absolutely fundamental to the creative process of modern programming. Rust breaks this cycle systematically and pervasively. We're not talking about additional seconds that can be ignored. We're talking about waits that qualitatively change the entire development experience and the way programmers can work creatively. A medium-sized Rust project typically requires 2, 3, 5 minutes for a complete compilation. Enterprise-sized projects can require 15, 20, even 30 minutes or more. Compare this with the experience of other languages. Go compiles enormous projects in a few seconds. C# with hot reload allows practically instantaneous changes during debugging. Python and JavaScript offer immediate feedback. Even C++ with all its historical problems has incremental compilation that often beats Rust significantly. There is consolidated psychological research that demonstrates how waits of more than 10 or 15 seconds completely interrupt flow state, that state of deep and immersive concentration that is absolutely essential for complex and creative programming. When every small modification, every experiment, every optimization attempt requires minutes of waiting, the programmer inevitably loses the thread of thought. The mental process of keeping in mind the problem state, possible solutions, architectural implications, all of this dissolves during forced waiting. The result is that instead of rapidly iterating on creative ideas, experimenting with different approaches, exploring innovative solutions, the programmer is forced into batching modifications, drastically reducing experimentation and exploration. The software that emerges from this process is necessarily more conservative, less innovative, less optimized than what it could be with immediate feedback. Rust's compilation times have direct and measurable economic costs that are often ignored in comparative evaluations. First, infrastructure costs. More powerful and expensive build servers, slower continuous integration pipelines that block deployments, cloud compute that scales up to handle compilation-intensive workloads. Second, human productivity costs. Developers waiting instead of producing value, meetings interrupted by compilation time, constant context switching that reduces cognitive efficiency. Third, iteration costs. Fewer test cycles means more bugs reaching production, slower debugging, more complex quality assurance. I've seen teams calculate that Rust's compilation times effectively cost 20, 30, even 40% more compared to alternatives like Go or C# for projects of equivalent size and complexity. This isn't a theoretical cost, it's a real cost that appears in budgets and project timelines. Rust promises that long compilation times are investments that pay significant dividends in runtime performance. But this promise is often illusory in the real practice of software development. Most modern applications are fundamentally I/O-bound, not CPU-bound. They wait for databases, networks, file systems, user input. In these contexts, the performance optimizations that Rust provides are irrelevant or marginal. Profile-guided optimization in other languages can often achieve equivalent performance when necessary. JavaScript engines like V8 and Java runtimes like Hotspot have just-in-time compilation that in many practical cases surpasses static Rust code because they can optimize based on real usage patterns instead of compile time assumptions. We're paying a certain and immediate cost, compilation time, for an uncertain and often unnecessary benefit, runtime performance that we might not need for our specific domain. Fred Brooks, in his classic essay No Silver Bullet, makes a crucial distinction between essential complexity and accidental complexity. Essential complexity is intrinsic to the problem you're trying to solve. It's the inherent difficulty in your business domain. Accidental complexity is an artifact of the tools you use to solve the problem. It's difficulty that ideally shouldn't exist. Rust's lifetimes are the purest example of accidental complexity I have ever encountered in decades of programming. They don't exist because the problem domain requires them. They don't exist because they represent natural concepts in software architecture. They exist exclusively because Rust's specific design requires them to satisfy the internal constraints of its type system. Lifetimes in Rust start as a seemingly simple concept, expressing how long a piece of memory remains valid. But this superficial simplicity hides a combinatorial complexity that explodes rapidly in real projects. Consider a function that seems innocuous, returning the longest string between two inputs. To do something conceptually immediate, You suddenly have to introduce a generic lifetime parameter that expresses an abstract temporal relationship between input and output. You're declaring to the compiler that the output's lifetime cannot exceed the parameter's lifetime. But this is just the beginning of the complexity explosion. When functions compose, when data structures nest, when architecture grows, lifetimes multiply and interact in ways that become rapidly incomprehensible even for experienced programmers. A real function in a mature Rust project can have 4, 5, 6 generic lifetime parameters with complex dependency relationships expressed through where clauses that occupy more lines than the actual business logic code. This is no longer code. It's a type theory treatise disguised as software implementation. Rust supporters argue that lifetimes make code more expressive because they make explicit the temporal relationships that in other languages remain implicit. But expressiveness in programming means communicating intentions and concepts clearly and concisely. When 70% of your code consists of lifetime annotations describing artificial temporal relationships, where have the business logic intentions gone? Where is the communication of your domain's central ideas? True expressiveness has been lost in a sea of theoretical boilerplate. Compare with languages that manage memory automatically. The programmer expresses what they want to accomplish, what transformations to apply to data, what logic to implement. They don't have to express when every piece of memory lives and dies, how objects relate temporally, what precedence constraints to respect. The result is code that communicates domain intentions instead of type system implementation details. It's the difference between prose and technical documentation. Both communicate information, but one is readable and the other is reference material. Rust convinces its users that lifetimes are necessary for memory safety, that without explicit duration annotations, it's impossible to guarantee correctness. But let's look at the alternatives that exist in the real world of programming. Garbage collection in languages like Go, Java, C# manages arbitrarily complex memory relationships without ever requiring the programmer to think explicitly about lifetimes. RAII and smart pointers in modern C++ eliminate manual management for the vast majority of cases without verbose annotations. Automatic reference counting in Swift manages ownership automatically in most situations. Research languages show even more automatic approaches: region-based memory management, more sophisticated linear type systems, high-performance incremental garbage collection. The existence of these alternatives demonstrates that lifetimes are not intrinsically necessary. They are necessary only if you choose Rust's specific and idiosyncratic approach. Lifetimes require the programmer to mentally maintain an extremely complex temporal model of how data flows through the program over time. This model must be accurate not only for the logical correctness of the software, but also to satisfy the arbitrary constraints of the type checker. The result is that a significant part of mental effort during development is dedicated to a problem that other languages have solved automatically and transparently. It's like driving a car where you have to manually calculate when to fire each cylinder, what fuel mixture to use for each piston stroke, how to coordinate the timing of each valve. Technically, it's possible, and maybe it gives you theoretically superior control. But why would you want this complexity when automatic systems exist that handle these details transparently and efficiently? Rust promises safer and more readable code through explicitness and strong typing. But readability in programming means communicating intentions clearly and concisely. When code is dominated by syntactic boilerplate necessary to satisfy the type system, the real intention gets lost in the noise. Consider a concrete example from daily programming. We want to read a JSON configuration file and extract a specific value with a sensible default. In concise languages, this operation is expressed in a few intuitive lines that directly communicate the intention. In Rust, the same operation explodes into explicit error handling, multiple type conversions, verbose pattern matching, and utility method calls. The signal-to-noise ratio is drastically different. In concise languages, every line expresses meaningful business logic. In Rust, most of the code handles conversions, error handling, and type safety, all overhead required by the language, not by the problem you're solving. Rust has an incredibly rich but rigid type system. The practical result is that programmers spend a disproportionate amount of time converting between types that are conceptually identical but technically distinct in Rust's system. Strings are the most flagrant example. You have owned string slice references, string literals, cowstring types, OS string for interoperability, path and path buff for file system. Every conversion between these types is technically necessary for the type system, but conceptually you're always manipulating the same fundamental concept, a sequence of characters. The same pattern repeats with collections, numeric types, error types, async types. The programmer spends significant time navigating the type taxonomy instead of implementing business logic. Rust forces explicitness on details that in other languages are automatically inferred or handled transparently by the runtime. Every operation that can fail requires explicit handling through result types and pattern matching. Every variable must explicitly declare whether it's mutable. Every data passing requires explicit decisions about clone versus move versus borrow. This explicitness has theoretical advantages in terms of control and predictability, but enormous practical costs in terms of development speed and cognitive load. The programmer spends more time communicating with the compiler than solving real domain problems. The irony is that this explicitness often doesn't lead to greater clarity. When every operation is surrounded by explicit boilerplate, the operations that are really important, those that require special attention, get lost in the general noise. Verbose code is not just slower to write initially, it's significantly harder to maintain over time. When you have to modify a Rust function, you often have to simultaneously modify the type parameters, lifetime annotations, type conversions, error handling, and only at the end the actual business logic. In more concise languages, changes to business logic often require only changes to business logic. The rest is handled automatically by the type system or runtime. The result is that simple and localized modifications in Rust become complex refactorings that touch multiple parts of the codebase. This maintenance overhead accumulates over time. Mature Rust projects often develop a sort of architectural rigidity where even small changes require disproportionate effort to propagate through the type system constraints. Every programming language requires the programmer to mentally manage different levels of abstraction simultaneously. The domain problem with its business logic, the algorithms and data structures appropriate for implementing efficient solutions, the syntax and semantics of the language itself, performance and scalability considerations. Rust adds additional layers of mental complexity that must be constantly kept in mind. The ownership and borrowing system with its intricate rules, the lifetime relationships between different pieces of data, the deep implications of the type system, the conversions necessary between similar but distinct types. The result is that a significant fraction of cognitive resources is always dedicated to satisfying Rust instead of solving the real problem. It's like trying to compose music while someone constantly explains music theory rules to you. Both are valuable activities, but they interfere with each other when forced to happen simultaneously. Flow state, that state of deep concentration where programmers are most creative and productive, requires tools to become transparent. When the language demands constant attention to implementation details, flow breaks repeatedly. I have personally observed experienced programmers in other languages become visibly frustrated and less creative when working in Rust. Not for lack of technical competence or intelligence, but because the language demands such a large portion of their mental attention that little space remains for creativity and innovative problem solving. The cost of this interference is subtle but cumulative. Software developed under cognitive stress tends to be more conservative, less elegant, less optimized for the specific domain. Becoming genuinely expert in Rust requires learning complex memory models, advanced type theory, specific patterns for convincing the borrow checker, libraries, and crate ecosystem to compensate for core language limitations. This expertise is deep and sophisticated, but it's also strictly specialized, applicable only to Rust and its ecosystem. Compare with expertise in algorithms, software architecture, domain modeling, performance optimization, security, distributed systems, competencies that transfer between languages, technologies, and domains. The trade-off is not neutral. Time spent becoming expert in Rust ownership is time not spent becoming expert in distributed systems, machine learning, user experience, business strategy. The simple existence of the unsafe keyword in Rust is the most honest admission that Rust's safety system is not complete or absolute. But the problem is much deeper and more pervasive than this admission superficially suggests. Examine the source code of Rust's fundamental libraries, the standard library, collections, allocators, synchronization primitives. They are literally full of unsafe blocks. This means several things profoundly problematic for the safety narrative. First, the safety that Rust promises is fundamentally an illusion. Your safe code depends critically on foundations that are not safe. Safety is a layer of abstraction, not an intrinsic property of the system. Second, the complexity of memory management hasn't been eliminated. It has been hidden and concentrated. Someone still has to write code that manages raw memory, unchecked pointers, potentially dangerous operations. The responsibility has been shifted, not removed. Third, this concentration of unsafe code creates single points of failure potentially more dangerous than distributed memory management in traditional languages. Rust implements strangely contradictory logic. We don't trust you to manage memory directly in your specific domain that you know intimately, but we trust completely library authors who don't know your use case to implement unsafe abstractions that you will use blindly. This distribution of responsibility makes no logical sense. An expert programmer who knows their domain perfectly, their data flows, their performance requirements must fight with the borrow checker to implement an optimal solution. But a library author, writing generic code for use cases they can't completely predict, gets free rein to use unsafe constructs. The safety model becomes, don't trust domain experts, but trust library implementers absolutely. This is backwards from every principle of software engineering and security. Rust doesn't eliminate complexity, it moves it around. Memory management complexity that in C++ is distributed throughout the codebase becomes concentrated in unsafe library code. Error handling complexity that other languages manage with exceptions becomes explicit and pervasive through result types. Concurrency complexity that other languages handle with thread-safe data structures becomes explicit ownership and borrowing negotiations. I/O complexity that other languages abstract with high-level APIs becomes explicit lifetime management. The total complexity remains the same or increases, but it's redistributed in ways that make it less visible during initial development and more problematic during maintenance and scaling. The Rust community presents memory safety as a binary choice. Either you have the rigid constraints of Rust, or you have undefined behavior and security vulnerabilities. This is a false dichotomy that ignores decades of successful systems programming in other languages. Modern C++ with smart pointers, RAII, and sanitizers provides memory safety for the vast majority of use cases without Rust's complexity. Languages with garbage collection have essentially solved memory safety at the cost of some performance overhead that is often irrelevant in practice. Sanitizers, static analysis tools, formal verification, fuzz testing. There are many approaches to memory safety that don't require restructuring how we think about programming fundamentally. The question isn't whether memory safety is important. It obviously is. The question is whether Rust's specific approach to memory safety is worth its enormous costs in complexity, productivity, and cognitive overhead. My goal in this analysis is not to convince you that Rust is categorically bad or that it should never be used. Every tool has appropriate contexts and inappropriate contexts. My goal is to encourage a more honest discussion about the real trade-offs involved in choosing Rust. The current discourse around Rust is dominated by enthusiasm and promotion that minimizes or ignores these trade-offs. We hear constantly about memory safety and performance benefits, but rarely about the months of reduced productivity, the cognitive overhead, the architectural constraints, the maintenance complexity. A mature engineering decision requires understanding both benefits and costs. Rust has real benefits in specific contexts. Systems programming where memory safety is critical, performance-sensitive applications where garbage collection overhead is unacceptable, security-sensitive code where additional constraints provide real value. But Rust also has real costs that are often hidden or minimized. Extended learning curves, reduced development speed, increased cognitive load, architectural rigidity, maintenance overhead. Rust makes sense when its benefits clearly outweigh its costs for your specific context. If you're writing an operating system kernel, a cryptocurrency implementation, a high-frequency trading system, a memory-critical embedded application, contexts where memory safety and performance are absolutely critical and where the development time investment can be justified. Rust makes less sense for typical business applications, web services, data processing pipelines, user interfaces, contexts where development speed and maintainability are more important than marginal performance improvements or theoretical memory safety guarantees. The problem is that Rust is often promoted as a general-purpose solution for problems where its costs clearly exceed its benefits. My deepest concern about Rust is not its technical characteristics, but its impact on innovation in the programming language space. When the industry becomes convinced that Rust represents the pinnacle of language design, we stop looking for better solutions. There are promising research directions that could provide memory safety without Rust's complexity. Automatic memory management with better performance characteristics, more sophisticated type systems that infer constraints instead of requiring explicit annotations, hybrid approaches that combine different memory management strategies within the same language. But research and innovation in these areas receives less attention and funding when the community believes the problem has already been solved definitively. Programming languages are tools, not religions. They should be evaluated pragmatically based on their suitability for specific tasks, not promoted dogmatically as universal solutions. Rust is an interesting experiment in language design that has contributed valuable ideas to the field. Its approach to memory safety without garbage collection is technically impressive and has inspired important research. But Rust is not the end of programming language evolution. It's one point in a vast space of possible designs, with its own unique trade-offs and characteristics. The industry will be healthier when we can discuss these trade-offs honestly, when we can acknowledge both Rust's innovations and its limitations, when we can choose tools based on technical merit rather than community enthusiasm. Programming is fundamentally about solving problems efficiently and creatively. Any tool or philosophy that interferes with this fundamental goal, regardless of its theoretical elegance or community popularity, deserves critical examination. My hope is that this analysis contributes to a more nuanced and honest conversation about Rust's place in the programming language ecosystem, free from both uncritical enthusiasm and unfair dismissal. The goal is not to tear down Rust, but to understand it clearly enough to use it appropriately and to continue innovating beyond it.